So we're going to work on identifying linear functions. We're going to be able to identify if a function is linear by looking at a graph, by looking at a table of values, and also to see if we can write the function in standard form. And then we'll work on writing those in standard form. All right, so does this graph represent a function? So we know from our studies before that if we have one domain value matching with one range value, then we're in good shape. And the only thing we've added now is this a line? That's what makes it linear. So yes, it's a function, and indeed this one is a linear function. Here we have a function. Every x value has just one y value. I could do my vertical line test, but in fact it doesn't graph a line. So this is not a linear function, but it is a function. And here, do I have a function? Well, I've got an x value of -2 that is associated with multiple y values. So I do not have a function. It is a line, so it's linear, but it is not a function. All right, so I told you we'd look at graphs to see if they were linear functions. Now we're going to look at a set of points in this table to determine if it is a linear function. Well, we're going to look for a pattern. And if I look at my changes in x, I'll notice that every time I'm adding 2, adding 2, adding 2. So my change in x is constant. My change in y is also constant. So the fact that I have a constant change in x and a constant change in y, that means I have a linear function. So we're going to tell whether the set of ordered pairs satisfies a linear function. All right, first of all, I'm going to have to put my values in here. And I am looking to see if there is a pattern. Is there a constant change in x and a constant change in y? Well, what do I see? I've got +2, +2, +2, +2. So far, so good. What about over here? I've got -12, -4, +4, +12. Okay, so I do have a function, but this is not linear. I do not have a constant change in x and a constant change in y. So these points do not satisfy a linear function. All right, so another way to determine whether a function is linear is to look at its equation. If I have a linear equation, it can be written in standard form. So if I can write an equation in standard form, and that is ax plus by equals c, if I can write it in standard form, then it is a linear equation. Now, a, b, and c have to be real numbers, and a and b cannot both be 0. So let's look at a few more definitions of what we can and cannot have. X and y both have to have exponents of 1. That means I've got, plain old x, plain old y. I cannot have x squared or y squared. It has to be an exponent of 1. X and y are not multiplied together. I cannot have a value that is xy. And x and y do not appear in denominators, exponents, or in radical signs. So here's some examples of what is linear. 3x plus 2y equals 10. That is in standard form. That's perfect. This one we can rearrange to write it in standard form. This one too can be rearranged to write in standard form. Here are the standard forms. We're going to talk about this in a minute. These, I've got an xy multiplied together, so that is not linear. I've got a exponent other than 1, not linear. And here I've got a variable in my denominator, also not linear. All right, so is this function linear? Yes, it's written ax plus by equals c. How about here? Nope, I've got an x times y. That's not going to work. How about here? Y equals 12. In fact, this is going to be a linear equation because this equation could be written in the standard form ax plus by equals c, where, a equals 0. So I've got 0x, but I have 1y, and that equals 12. All right, so now we're going to talk about actually writing equations in standard form, because a lot of times you're going to see equations like this, y equals 9x plus 2, but I need to move this around so that it is written in standard form. So remember, a and b cannot both be 0, and in the end I'm not going to be able to have a negative a. So my x, the coefficient on my x, will always have to be positive, and I'm also going to need to clear all fractions from my equation. Everything has to be a whole number. So let's look at changing this to standard form. Well, I've got y equals 9x plus 2, and remember I need to keep my x positive. So what I'd like to do is I'd like to move my y over to this side so that I don't have to deal with a negative x. So I'm going to subtract my y on both sides, and I get 0 equals 9x minus y plus 2. I'm going to have to subtract 2 from both sides, and I get negative 2 equals 9x minus y. Of course, I can rewrite this with the moving them on the other side of the equation, equal sign, which gives me 9x plus, 9x minus y equals negative 2. This is written in standard form. We're going to try that again. I've got y equals 7x minus 7. Well, if you think you already know how to do this, go ahead and pause the video. If you don't, watch me again. So I'm going to remove my y, move it over to this side of the equation, and I get 0 equals 7x minus y minus 7. Add 7 to both sides, and I get 7 equals 7x minus y. I'm going to rewrite that as 7x minus y equals 7. Okay, pretty straightforward. Now, okay, so this one is a little bit more complicated because I've got a fraction here as my coefficient of my x variable. But notice, because it's negative, I can actually add it to both sides this time. And if I add, I'm going to end up with a positive x on the left-hand side, which is what I want. So 7/4 x plus y equals negative 1. All right, but I can't have a denominator. I can't have a fraction. So to clear this fraction, remember I multiply by the common denominator, okay, which is 4. And those are going to cancel out, so I have 7x plus, remember I'm distributing, okay, don't forget this part, 4 times y, 4y equals negative 4. This is now in standard form. 7x plus 4y equals negative 4. All right, if I want to graph a function, I can do that by choosing values. We've done this before. I'm just going to go ahead and quickly put this together. My function is y equals x plus 2. I've picked a couple of points. Remember, I usually pick negative 2, negative 1, 0, 1, 2 because they're just useful, helpful, friendly. So I'm going to plug in for each one. Okay, and then I can graph my ordered pairs. Negative 1, 1, 0, 2, and 1, 3. And notice this will, in fact, create a line, albeit not very neat. And it's going to include all points. Notice I did not have a limited domain. I just picked these points. So in fact, it has a connecting line with arrowheads at both ends. Okay. Real world example. I like these. Bianca rents a space at a farmer's market and pays the market manager $6.50 for each gourd that she sells. The amount Bianca pays each day is given by the function f of x equals $6.50 times x, where x is the number of gourds sold. I want to graph the function and then give its domain and range. And this would have been helpful on our last test and quiz. So remember, this is a real world, so I'm not going to be able to have negative x's because I'm not selling negative gourds. So I'm going to try 0, 1, 2, and 3. If I sell 0 gourds, remember my equation right up here. If I sell 0 gourds, I make $0. If I sell 1 gourd, I make $6.50. 2 gourds give me $13. 3 gourds give me $19.50. So I am just selecting points to graph. My graph will look something like this. It's all going to be in quadrant 1, where I've got numbers of gourds and the amount she makes. So 0, 0, 1, 650, 2, 13, 3, 1950, and I could have labeled those points. Therefore, my domain, as we've seen from before, would be 0, 1, 2, 3, and my range then would be 0, 6.5, 13, 1950, etc. Okay, so remember, and those are discrete values, so I am not going to connect my graph. All right, that was it. We'll see you all on Monday.